Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 asks, how many milliliters are in 4.7 gallons? And they also gave us some useful conversion factors, such as 1 gallon is equal to 3.8 liters. So let me write this down. And we also know that 1 liter is equal to 1,000 milliliters. Okay, so when doing conversion factor questions, it's always helpful to write these down just so that you can see what you're working with. And then we always start off with the units, obviously, that we start with, which is 4.7 gallons. And we want to go from gallons to liters, and then from liters to milliliters. So when changing from one unit to the other, when we multiply by conversion factors, we want our desired units at the top. So in this case, liters. And we want the units that we want to get rid of at the bottom. That way, when we multiply it out, then our units for gallons will cancel out. So now we'll have an answer in liters, but we also, the question asks for the answer in milliliters. So we can do this in the same step, just by multiplying again by our conversion factor, and our desired units for milliliters will be on top, so 1,000 milliliters. And then our units that we're trying to get rid of is at the bottom. So in this case, it's liters. And now we can multiply it all out. So 4.7 times 3.8 times 1,000 gives us 17,860 milliliters. We can say are in 4.7 gallons. Okay, so let's see what the junior tutor said. To convert into milliliters, first calculate the number of liters present, and then finally convert the liters into milliliters. To convert gallons to liters, multiply the gallon value by 3.8 liters. Yep. And then to convert liters to milliliters, just multiply the liters value by 1,000. Okay, so they also got 17,860. So this solution is correct. Okay, so question number 2. A buffer solution based upon sulfurous acid, which is H2SO3, was created by treating 1 liter of a 1 mole per liter sulfurous acid solution with sodium hydroxide until a pH of 1.611 was achieved. And we assume no volume change. To this buffer, 1.25 moles of sodium hydroxide were added. Also, we need to assume there's no volume change. And what is the final pH of this solution? Okay, so this is actually a very long multi-step question, but we'll tackle each step one by one. So the first thing I like to do when we do buffer questions is to think about all the steps that they took in order to create the solution. And you need to realize what reacts with what and how much of it is left over that carries on to the next step. So for example, we know that a buffer solution that was based upon sulfurous acid, which is H2SO3, it was created by treating 1 liters of it with sodium hydroxide. So first, let's show the reaction of H2SO3 when it dissociates into its ions. And this is a polyprotic acid, so that means it can lose its first proton and become HSO3 minus. And after this step, it can also lose its second proton. But for this first part of the question, let's just lose the 1 proton. And this will have a certain Ka value. So let's search just Ka values. And we can find just like a table. I'll try to be specific. H2SO. I'm trying not to click on one that has the same type of question. So this is the one I looked at earlier. So you'll see sulfurous acid here. Its Ka1 value is equal to 1.5 times 10 to the negative 2. So I'm just going to write that down. Ka1 is 1.5 times 10 to the negative 2. And the reason I wanted to find the Ka value is so that I can also calculate pKa 1. So the equation for pKa is equal to the negative log of our Ka value, which is 1.5 times 10 to the negative 2. And then I can calculate the pKa of this reaction to be 1.824. Okay, so now I have the general reaction that occurs when sulfurous acid first deprotonates into its ions. And now I can see what happens when it is treated with sodium hydroxide. So let me do this in a different color. So now I can say after treating with NaOH, I can write the following reaction equation where H2SO3 reacts with a hydroxide ion to form water plus HSO3 minus. Okay, so now let's construct an ice table where our initial concentrations for H2SO3, it's 1.00. And we don't know how much sodium hydroxide was added, so I'm just going to put a question mark. Water is a liquid, so this won't be included in our ice table. And the concentration of SO3 minus at the beginning of the reaction is 0. So now the change will be negative X for H2SO3, and the change for the hydroxide will be however many of the moles of the sodium hydroxide was added. So we don't know how much was added, but we can say that the change for HSO3 minus is plus X. And the reason why I didn't put the change for my hydroxide is because at equilibrium, we know that for H2SO3, it will be 1 minus X. And for the hydroxide, it's just going to be 0 because we added it until a certain pH. And also because the hydroxide ion won't be included in my pH equation, which I'll write in a bit. That's why we're also not really interested in its equilibrium concentration. So we're basically only interested in H2SO3 and HSO3 minus. So now from here, I can show that the pH is equal to pKa1 plus the log of our conjugate base, which is HSO3 minus, divided by the concentration of H2SO3. And they said that the pH was 1.611, and we know the pKa was 1.824 plus log. And then for the concentration of HSO3 minus, I'm going to sub in my X divided by 1 minus X for the concentration of the acid. So now all we have to do is solve for X. So to get rid of the log, we would do 10 to the power of these values. So I'm just going to simplify it down here. You should end up getting X over 1 minus X is equal to 0.6124. And then when we finally solve for X, you should get around 0.38. Okay, so what this 0.38 means is that it is the moles of HSO3 minus. And this is also if we assume 1 liter of solution, just to make it easier to convert from concentration to moles. So I'm just going to say that up here. So if 0.38 is the moles of HSO3, we know that 1 minus 0.38 is equal to 0.62. And this is the moles of acid that we have left over. Okay, so this is only the first part of the question. And I'm just going to start a new page. And now we can move on to reaction 2. So now we can say after 1.25 moles of NaOH is added. So now this is the second step of our reaction where they add more NaOH. So we can have the same reaction occur where we have that leftover H2SO3 plus, and this time we know how much sodium hydroxide was added. Makes H2O plus HSO3 minus. Okay, so now we need to have the remaining moles of H2SO3 from the previous question, which was 0.62. And we also have some concentration of our HSO3 minus ion from the previous step as well, and we calculated it to be 0.38. Again, I'm just going to neglect the water, but this time for the OH minus, we know that 1.25 moles were added. And this time the change is just going to be occurring, like the reaction only occurs until we run out of our reactant, our limiting reagent, which is H2SO3. So for the change, I'm just going to say minus 0.62. So the OH only reacts until the H2SO3 minus runs out. So again, we say minus 0.62. And this gives us 0.63. And in the case of our HSO3 ion, it's going to react with the sodium hydroxide. So we're going to add 0.63. So this is what we got from here. And now its new concentration is 1.01. Okay. So after this takes place, since again this is a polyprotic acid, we're going to have this conjugate base react with any of the excess OH from the previous step. So for this reaction, we have our conjugate base reacting with the leftover OH minus to form water plus SO3 2 minus. So this will have a different Ka value. So this is where the Ka2 comes in. So now let's look at our table again. Ka2 is equal to 6.3 times 10 to the negative 8. And now we can calculate for pKa, which is the negative log of this Ka value. And you should end up getting around 7.2. Okay, so now let's construct this last ice table. So our conjugate base, we know from the previous question, was 1.01. It reacts with 0.63 moles of the OH to produce water. Again, we're not going to count this in our ice table. And the initial concentration of SO3 2- is 0. And for the change, the HSO3- will only react until the hydroxide ion runs out. So for the change, it's going to be negative 0.63. And the same thing for the change in the hydroxide, 0.63, just until it runs out. And the change for the SO3 2- will be plus 0.63. Okay, so now for equilibrium, we get 0.37. The hydroxide ion is now 0. And for SO3 2-, you get 0.63. So now we need to know the pH of this final solution. So pH is equal to the pKa. So this time we are concerned with pKa2 plus the log of the concentration of our conjugate base divided by the concentration of our acid. And plugging in pKa, we get 7.2 plus log 0.63 divided by 0.37, and we get a final pH of around 7.43. Okay, so this is our final answer. And let's see what the junior tutor said. Buffer systems are solutions that resist drastic changes in pH whenever an acid or a base is added to a solution. They can resist drastic changes in pH at a certain pH range, which is called the buffer capacity. Buffer system is usually achieved by the mixture of a weak acid and its conjugate base in salt form, or a weak base and its conjugate acid in salt form. Find the pH of a buffer solution, we can use the Henderson-Hasselbalch equation. Okay, so this is true. But they have a different pKa value, which is okay because some sources give different values. But already you can see here that they just did it in this one step. Which we know is incorrect because there's a lot more that occurs to answer this question. So I'm going to try my best to answer this in text form without any ice tables, so bear with me. Okay, so I said the definition definition for buffer system, and the Henderson-Hasselbalch equation is correct. However, the solution is incorrect. Assuming we have a volume of 1 liter, and if the Ka1 is equal to 1.5 times 10 to the power of -2, and Ka2 is equal to, I said the 6.3 times 10 to the power of -8. After initially treating with NaOH, we have 0.38 moles of HSO3 minus and 0.62 moles of H2SO2 or H2SO3 left over. Okay, so that was the first part of the question. Let me just also say we need to construct different ice tables to get these answers. And then after 1.25 moles of NaOH is added, we have 0.63 moles of SO3 2 minus formed, and 0.37 moles of HSO3 minus left over. Oh, I didn't even do the step before that, sorry. We have 1 point. Wait, let me keep this sentence for later. Okay, so we have 1.01 moles of HSO3 minus formed, and 0.63 moles of OH minus left over. Finally, after the leftover OH minus reacts with HSO3 minus, then we have 0.63 moles of SO3 2 minus formed, and 0.37 moles of HSO3 minus left over. To solve for final pH, using the Henderson-Hasselbalch equation, solve for final pH. we get around 7.43. Okay, so hopefully this makes sense in the text form, but I would say this video would be easier to get the solution for this question. So the solution was actually incorrect this time. Okay, so question number 3. Classify the following as polar or nonpolar. So to answer this question, we need to just draw all of the different Lewis structures of these molecules, and then from there we can try to figure out if they're polar or nonpolar. So first, let's find the total valence electrons for our first molecule. I think this is germanium. We hardly see this element, so that's why I'm kind of hesitant on what it's called, but this is germanium, I'm pretty sure. And look up a periodic table. It is found right here, atomic number 32, in 14, in group 14, so it has 4 valence electrons. And for hydrogen, hydrogen has 1 valence electron, and we have 4 hydrogens, so we just multiply this by 4. And we should just get a total of 8. So if we draw out the Lewis structure, we have our germanium in the middle. And then we just have our 4 hydrogens single bonded. And if we count out all the electrons I've drawn so far, you'll see that I already have my 8. And you'll also see that everything is symmetrically around the germanium, all the hydrogen atoms. So therefore, this molecule is nonpolar. So you can see that I didn't even need to calculate for electronegativity. Even just the fact that it's a symmetrical molecule, I could say that this is a nonpolar molecule. Because even if there was a difference, then they would all just cancel each other out. Okay, so on to our second compound. We have water, H2O. Okay, so again, hydrogen has the 1 electron multiplied by 2. Oxygen has 6 valence electrons. And we get a total of 8. So now let's draw oxygen as our central atom. And then we'll have our 2 single bonded hydrogens. So you'll see that when if we recall that each bond contains 2 bonding electrons, that means I only have 4 electrons in this structure so far. So for the remaining 4, since we need 8 in total, I'm just going to place them as lone pairs on my oxygen. So now notice that we have this bent structure. So it's not linear. And also, oxygen is more electronegative than the hydrogens. So we are going to see a dipole moment going towards the direction of oxygen. And because of its bent structure, it doesn't really cancel out or anything. So we're left with this partially negative side and partially positive side of the water molecule. So this is what makes water polar. Therefore, polar molecule. And this is because this dipole moment isn't cancelled out due to this structure of water. So now let's do our last molecule, which is carbon dioxide. Carbon has 4 valence electrons. Oxygen has 6. And we have 2 oxygens. So 12 plus 4 is 16 electrons in total. So now we'll show our carbon in the middle as our central atom. And then if we were to draw 2 single bonds to oxygen, then our carbon wouldn't have a full octet. So then we can just make these double bonds. And we only have 8 electrons in this structure so far. So we need 8 more. And the last 8 will go on my oxygens. Okay, so now for the case of, for this molecule, our oxygens are still more electronegative than carbon, so there's going to be dipole moments going towards the direction of the oxygens. But this time they cancel each other out. So we have a linear molecule. And these dipole moments cancel out. And when that happens, we have something called a zero net dipole moment. So therefore, we can say that CO2 is nonpolar. Okay, so now let's see what the junior tutor said. Polar molecules are those that have an electronegativity difference between the bonded atoms. On the other hand, nonpolar molecules are those that have electrons that are shared equally between atoms. There are also nonpolar molecules that have polar bonds in a larger molecule that cancel each other out. So for our first molecule, it's nonpolar. And they also calculated electronegativity difference between the two. And it says, though there's some electronegativity difference, the polar bonds cancel each other out due to their molecular geometry. For water, it's polar. And it says, though the overall charge of the molecule is neutral, orientation of the 2 positively charged hydrogens at one end and the negatively charged oxygen at the other end gives it 2 poles. So it's not actually positively charged like these aren't ions. We refer to them as partially positive. So I'm just going to kind of fix the wording for the second explanation. And for CO2, though there's an electronegativity difference between carbon and oxygen, the polar bonds cancel each other out due to the molecular geometry. Okay, so this solution is correct. For H2O, the hydrogens have a partially positive charge and the oxygen has a partially negative charge. Since oxygen is more electronegative and for CO2, the dipole moments cancel each other out. So this solution is still correct. Okay, so question number 4. Draw the Lewis structure for CO2 and discuss the Vesper for carbon. So when drawing Lewis structures, we first need to find the total number of valence electrons. So for carbon, there are 4 valence electrons. And for oxygen, there's 6. And we have 2 oxygen atoms, so we multiply this by 2. And we end up with 16 valence electrons. We start off writing the skeletal structure with our carbon as our central atom. And then I'm just going to draw 2 bonds to the 2 different oxygens. And notice that the carbon doesn't have a full octet yet. I'm just going to make these double bonds. And then for the remaining 8 electrons, we will add them as lone pairs on our oxygen atoms. So now let's analyze its Vesper shape, so its molecular shape and its electron geometry. And to do that, we need to look at the central carbon atom for this molecule. So carbon has 0 lone pairs. And it has 2 bonded atoms. So now let's look up a Vesper table, or Vesper chart, to help us analyze its shape. So when we have 0 lone pairs and 2 bonded atoms, we have both a linear molecular shape and electron geometry. And what the Vesper chart also tells us is that the carbon is sp hybridized, and that the bond angle is 180 degrees. Okay, so now let's see what the junior tutor said. They have the correct Lewis structure. Central carbon atom has 2 bond pairs and no lone pairs, for a total of 2 electron groups. Thus, the electron group for geometry is linear. According to Vesper theory, CO2 is of type AX2, which leads to a linear molecular geometry. Okay, so the solution is correct. I'll also mention that the carbon is sp hybridized, and the bond angles are 180. Okay, so question number 5. Is carbon disulfide polar or nonpolar? So first let's draw out its Lewis structure. And first we're just going to find the total number of valence electrons for this molecule. Carbon has 4 electrons. Sulfur has 6. And we have 2 sulfur atoms, so we multiply that by 2. And we end up with 16 valence electrons. So now carbon will be our central atom. And then I'm just going to draw 2 single bonds to my sulfur. And notice that carbon doesn't have a full octet yet, so let's just make these double bonds. And if we look at how many electrons I've drawn so far, each bond contains 2 bonding electrons. So we have 8, and I need 16 in total. So for the remaining 8, I'm just going to place them on my sulfur atoms. Okay, so now we're left with the following Lewis structure. And if we analyze this, carbon has 0 lone pairs and 2 bonded atoms. So using our Vesper table, we can find out its molecular shape, which is linear. And also its electron geometry is linear as well. So there is some electronegativity difference between carbon and sulfur, but even then, because of its symmetrical shape, these electronegativity difference would cancel each other out. So therefore, this is a nonpolar molecule. Okay, so the junior tutor said covalent bonds become polar because of the electronegativity difference between the elements involved. So they talk about electronegativity, how you can calculate the dipole moment. And it's actually noted that carbon and sulfur have the same electronegativity. So their bond is actually nonpolar. And when you have a molecule that's made up of all nonpolar bonds, then the entire molecule will just be nonpolar. So this solution is correct. I'm also going to add that CS2 is linear and symmetrical, which also indicates a nonpolar molecule. Okay, so question number 6. What is the name of SO3? So if we analyze this compound, we'll see that it's made up of 2 nonmetals. So we can say that this compound is binary covalent. And when naming binary covalent compounds, we would first name our first element, which is the sulfur. And then we would indicate how many atoms of our second element is there by using the Greek prefixes. So we would do the same thing for the sulfur, but when there's only one of it, we don't say mono, we just kind of assume that there's one of it. That's why I just said sulfur. For the oxygen, we put a tri in front of it. And then we start to write out the name of the second element, except this time it's going to end in "ide." So it's going to be sulfur trioxide. And the junior tutor said that in naming binary compounds, the most metallic element comes first with its elemental name, and the nonmetal would be the second element with its elemental name ending in "ide." Prefix is added to the second element indicating its number of atoms. Therefore, the name is sulfur trioxide. So the name is correct. But however, I think they described an ionic compound. For binary covalent, we would use a prefix for the first element, except if it is 1. Or except if there is only. Okay, so I'll still say this solution is correct, but I just added my note about binary covalent compounds. Okay, so question number 7. Why is why is an HCl molecule polar but a Cl2 molecule is nonpolar? So HCl, let's draw its Lewis structure. Hydrogen has 1 electron, fluorine has 7. So its Lewis structure would just simply be single bonded hydrogen to the chlorine. And I can show all the lone pairs on chlorine as well. And the reason why this molecule is polar is because chlorine is so much more electronegative than the hydrogen that we have a non-zero dipole moment pointing towards the direction of chlorine. So now we can show that the hydrogens are partially positive, the chlorine's partially negative. So therefore, this molecule is polar. But if we were to compare it with Cl2, we just have a diatomic chlorine. And then we can show the lone pairs. And every time you have a diatomic molecule, this means that it's also nonpolar. And the reason why is because these chlorine atoms have the exact same electronegativity, so they're going to cancel each other out. So we can say that we have no dipole moment because they cancel each other out. So therefore Cl2 is nonpolar. Okay, so the junior tutor said that a polar covalent bond is created when the shared electrons between atoms are not equally shared. This occurs when one atom has a higher electronegativity than the atom it is sharing with. As a result, the shared electrons will be closer to the atom with the higher electronegativity, making it unequally shared. Bond polarity is the separation of electric charge along a bond. However, the electronegativity difference between chlorine atoms is 0. Therefore, the shared pair of electrons is attached equally to both chlorine atoms and remains exactly in the center, making chlorine-chlorine bond nonpolar. Since the chlorine atom is more electronegative than the hydrogen, the shared pair of electrons is attracted to the chlorine atom. This results in the chlorine atom acquiring a negative charge while the hydrogen atom acquires positive charge. Distribution of electrons across the molecule becomes uneven, making the molecule polar. I'm just going to add that they're partially negative and partially positive. Okay, but the solution is correct. Okay, so question number 8. Does ammonia, which is NH3, have ionic or covalent bonding? So when we have an ionic bond, this is between a metal and a nonmetal. And when we have like the giving or taking away of electrons, so electrons are added or removed, to form ions. However, for covalent bonding, this is between two nonmetals. And we have the sharing of electrons. So in the case of NH3, both nitrogen and hydrogen are nonmetals. So already we can say that ammonia has covalent bonding. Okay, so the junior tutor said that a chemical compound is a substance composed of many identical molecules of atoms of more than one element held together by a chemical bond, and be categorized into two according to how the constituent atoms are held together: ionic compound or molecular covalent compound. Okay, so they say that they are both nonmetals, so they share electrons. So this solution is correct. They had a very well explained explanation, but in the interest of time, I'm just going to briefly go through it. Yep, but the solution is correct. Okay, so question number 9. Part A, what elements are gases at room temperature? Name 6 of them. B, do these elements cluster in some part of the periodic table? Explain. Okay, so some elements can be gases at room temperature. So for example, helium, nitrogen, oxygen, fluorine, argon, chlorine. These are all the elements that can be gases at room temp. And it looks like the junior tutor kind of already mentioned where they are in the periodic table. So we have helium, nitrogen, oxygen, fluorine, argon, chlorine. They're kind of clustered at the top right of the periodic table. As we proceed to the right of the periodic table, the reactivity of the elements decreases. Also happens that their boiling point is low. That's why they are in gas phase at room temperature. Yep, so the solution is correct. Okay, so question number 10. Is carbon tetrafluoride polar? So first, let's draw the structure of carbon tetrafluoride. Carbon needs 4 bonds. So we have the 4 bonds to the fluorine. There are no lone pairs on the carbon. And we can just show all the lone pairs on the fluorines. And if we were to calculate the difference in electronegativity for carbon and fluorine, you'll notice that fluorine is much more electronegative than carbon. So because fluorine is more electronegative, the carbon-fluorine bond is polar. But if we look at the molecule as a whole, you'll notice that these dipole moments will cancel each other out. So the dipole moments cancel each other out. In carbon tetrafluoride. And we have a net zero dipole moment as a whole. So therefore, CF4 is a nonpolar molecule. So even though it contains polar bonds, because of the overall net zero dipole moment, the molecule is nonpolar. So the junior tutor said that the covalent bonds become polar because of the electronegativity difference between the elements involved. And then they just kind of give an explanation on electronegativity difference, how one can calculate the dipole moment. And they have the electronegativity of carbon is 2.5 and for fluorine is 4.0. So the difference between carbon and fluorine makes the carbon-fluorine bonds polar, partially positive charge on carbon, partial negative charge on fluorine. But the dipole moments cancel each other because of the tetrahedral arrangement of the bonds in the molecule. So in other words, the vector addition of dipole moments of the four bonds is 0. Therefore, carbon tetrafluoride is nonpolar. Yep, so that was a great answer. So the solution is correct. Okay, so those are all the questions for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. Also, if you enjoyed today's video, you can leave it a thumbs up and comment, or you could share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.